Lake Tahoe is sitting on top of a massive geologic powder keg, and the latest evidence suggests that the lake itself might be the one lighting the fuse. This is not speculation. It is happening right now. What researchers are calling an earthquake machine has been running at full capacity for the past few years. The weight of water pressing down on faults buried beneath the surface is doing something that seismologists are just beginning to truly understand. It is triggering earthquakes. And when you realize that 36 cubic miles of water is sitting directly above fractures in the Earth's crust, capable of 7.1 magnitude quakes that can generate 30-foot tsunamis, suddenly that beautiful alpine lake looks a whole lot more dangerous. This is the story that needs to be told. This is the mechanism that is reshaping our understanding of how the most serene landscapes on Earth can suddenly become catastrophic. Most people have visited Lake Tahoe. Most people think of it as one of the most peaceful places in North America. But beneath that crystalline surface, forces are at work that could change everything in seconds. The largest alpine lake in North America sits directly in the middle of an active seismic zone, and the water itself is the trigger. This is not ancient history. This is happening now. We're talking about the largest alpine lake in North America, 6,229 feet above sea level, over 300,000 acres of glittering water that has captivated millions of visitors for generations. The lake stretches 22 miles from north to south and is up to 12 miles wide at its widest point. The deepest part reaches over 1,600 feet below the surface, deeper than it is wide in some places. The lake's pristine beauty masks something darker, something geological, something unstable. But beneath that stunning surface lies a story that nobody is talking about. A story about how the lake itself is actively stressing the ground beneath it, pressing down with the weight of 36 cubic miles of water, lubricating ancient fault lines, and creating the conditions for a catastrophic earthquake that experts say could strike any time. Not in the distant future. Now, in the next earthquake cycle. This is the science of hydrostatic loading, and Lake Tahoe is ground zero for understanding how it works. Most people think of hydrostatic loading as something engineers worry about in dam construction. But Lake Tahoe isn't a dam. It's a natural basin that formed through tectonic violence and continues to be shaped by the same forces. The loading mechanism here is even more compelling because it's been happening continuously for hundreds of thousands of years, and we're only now understanding its true consequences. Geologists call this reservoir-induced seismicity. When you add massive amounts of water to a geologically active region, the faults respond. They become more active. They rupture more frequently, and the weight of that water can trigger earthquakes that wouldn't otherwise occur. 3 massive faults crisscross beneath Lake Tahoe like veins through a piece of marble. The West Tahoe Fault runs along the entire western shore, the most dangerous of the 3. This isn't just a minor crack. This is a 45-kilometer-long fracture in the bedrock, capable of rupturing with magnitudes that would devastate the entire region. Scientists have studied this fault extensively. They've mapped it. They've dated its ruptures using sophisticated radiometric analysis and paleoseismic trenching. They know what it's capable of. The vertical slip rate on the West Tahoe Fault is approximately 0.6 to 1.0 millimeters per year. That might sound tiny, but over millennia, it adds up to meters of movement, enormous displacement. The North Tahoe Fault cuts through the middle of the lake, separating the basin into distinct tectonic blocks. And the Genoa Fault on the Nevada side completes the network, forming a complex system of stress concentration zones. These aren't small fractures. These are major breaks in the Earth's crust that form what geologists call a graben. A graben is a rift valley, a depression formed when 2 pieces of the Earth's crust break apart and one or both sides drop down. Imagine 2 massive pieces of the Sierra Nevada and the Carson Range tilting away from each other, dropping down, leaving a valley between them. That valley, is where Lake Tahoe sits. That valley is where the stress accumulates. That valley is where earthquakes are born. The vertical displacement on these faults exceeds 400 meters in some places, nearly 1,300 feet of rock movement over geological time. That tells you how powerful these structures truly are. The basin is still actively subsiding, still dropping, at a rate measurable by modern GPS satellites that orbit Earth and measure ground movement with millimeter precision. The Earth is still moving here. Lake Tahoe formed not because of a meteor strike or some gentle geological process. It formed because of violent, ongoing crustal extension. The Sierra Nevada is still pulling apart from the Basin and Range province to the east. As those two massive pieces of the continent separate, the ground in between drops down. That subsidence created the basin. That same tectonic force keeps the faults active. Scientists call this extensional tectonics. The crust is being stretched like taffy, pulled in opposite directions. The process is ongoing. It hasn't stopped. It won't stop. The continent is literally tearing itself apart, and Lake Tahoe sits in the middle of that tear. This isn't a static geological feature. This is a dynamic system. And now, researchers understand that the lake sitting in that basin isn't passive. It's actively changing the stress state of those faults. The water weight isn't just adding pressure. It's redistributing stress in ways that make rupture more likely. This is where hydrostatic loading enters the picture, and it's where the real danger begins. The entire Tahoe Basin is what geologists call a half-graben, which means it's asymmetrical. The western margin, where the West Tahoe Fault runs, is the steepest and most structurally active. That's where the greatest stress concentration occurs. That's where the next major rupture is most likely to initiate. That's where the lake's weight matters most. The water doesn't load the fault evenly. It concentrates its stress on the deepest, steepest parts of the basin where the West Tahoe Fault plunges down into the earth. The fault plane itself dips at an angle of about 60 degrees, which means the water weight presses directly onto that inclined surface, increasing the stress that tries to make the fault slip. Scientists can calculate exactly how much stress each foot of additional water adds. Imagine a seesaw. On one side, you have ancient faults locked up by friction, held in place by the pressure of overlying rock. On the other side, you have something that looks innocent, water. But when you pour 36 cubic miles of water onto one end of that seesaw, the weight becomes astronomical. We're talking 151 trillion gallons. That number is so large it becomes abstract. So let's anchor it to something real. Picture an Olympic swimming pool. That pool is about 88,000 cubic meters of water. It's enormous. You could dive from the high platform and barely make a splash in terms of its volume. Lake Tahoe would fill 440 million of those pools. Not millions, hundreds of millions. The weight of that much water pressing straight down is beyond intuition. We're talking about 36 cubic miles concentrated in a basin that's only about 22 miles long and 12 miles wide. The water doesn't spread. It concentrates. The weight presses straight down. It doesn't spread out sideways. It goes straight through the rock and directly onto those faults. The water is concentrated. And as the weight increases, it does something counterintuitive. It actually weakens the faults. It increases the pore pressure in the rock, reducing friction, making it easier for the fault planes to slip past each other. Instead of the fault rocks being locked tight, the high pore pressure creates a hydraulic wedge. It's like putting a thin film of water between two pieces of sandpaper. Suddenly, they slide past each other much more easily. That's not just theory. Scientists have documented this mechanism in lakes around the world. It's been measured. It's been studied. It's repeatable. And it's absolutely real. The pressure increase from the weight of the water literally lubricates the fault, making rupture more probable. Seismometers have measured this happening in real time at dam reservoirs. The Kariba Dam on the Zambia-Zimbabwe border filled in the 1950s and 1960s, creating a massive reservoir. This wasn't a natural lake gradually accumulating water over millions of years. This was an artificial impoundment that raised water levels dramatically in just a few months. And something unexpected happened. Within months, scientists started detecting earthquakes directly beneath it. Not distant earthquakes right there, under the weight of the new water. Earthquakes that hadn't been happening before. The weight of the water triggered what's called reservoir-induced seismicity. Dozens of magnitude 5 earthquakes. In 1963, the Dam Valley experienced 80 magnitude 4+ earthquakes in a single month. 80. In a single month. It's happened at reservoirs in India, Canada, and Australia. Lake Mead behind the Hoover Dam experienced dramatic increases in seismicity when it filled. Seismologists tracked the pattern. As water levels rose, earthquakes increased. As water levels fell, earthquakes decreased. The correlation was unmistakable. The Aswan High Dam in Egypt triggered seismic swarms. Geologists watched it happen. They documented every earthquake. The pattern was identical. Every time humans fill a new reservoir, seismicity increases in predictable ways. The correlation is so strong that seismologists now expect it. They predict it before the reservoir fills. Some dams and reservoirs are specifically monitored because engineers know the water will trigger earthquakes. In some cases, dam operators deliberately manipulate water levels to try to prevent large earthquakes. The mechanism is real. The science is settled, and Lake Tahoe has been filling and draining for hundreds of thousands of years, with occasional extreme cycles that spike the stress dramatically. During ice ages, when the climate was colder and wetter, the lake rose to record levels. During droughts, it fell. Each time it rose, the faults experienced increased loading. Each time it fell, the load decreased. This pattern has been happening so long that it has literally shaped the landscape we see today. The West Shore drops so steeply because the West Tahoe Fault has been rupturing repeatedly over geological time, and water loading has been triggering those ruptures throughout that entire history. The fault has created a cliff, and the lake sits at the base of that cliff because the lake water creates the perfect conditions for the fault to rupture repeatedly. In 2023, something happened that put Lake Tahoe directly into the earthquake machine's sweet spot. The Sierra Nevada received the most massive snowpack in over 2 decades. We're not talking about a normal winter. We're talking about something exceptional. The numbers tell the story. 271% of normal snowfall in the northern Sierra. That's not an exaggeration. That's a scientific measurement from the water year measurements that California keeps meticulously. The highest levels since the state began consistent satellite measurements in 2000. This was the second snowiest winter on record for the region going back decades. The Central Sierra Snow Lab at Donner Pass received nearly 754 inches of snow. That's over 63 feet stacked on the ground. Imagine a 63-foot wall of snow. This massive accumulation was driven by an unusual weather pattern. Atmospheric rivers lined up like a conveyor belt. Storm after storm after storm, each one dumping moisture across the Sierra Nevada. Scientists called it epic. When that snowpack melted that spring and early summer, all that water flowed into the basin. The runoff was enormous. Rivers swelled, lakes filled, and Lake Tahoe received the full brunt of that wet winter's aftermath. Lake Tahoe, which had spent years in drought, seriously, years where the lake was well below full pool, sitting at historically low levels, suddenly surged to nearly 3 feet above full pool. The surface hit 6,227 feet, higher than it had been since the early 2000s. For context, the lake's normal full pool is 6,224 feet. Those 3 feet might sound small. They're not. 3 additional feet of water across 191 square miles of surface area, that's the entire lake surface, every single square mile, means an incomprehensible amount of weight pressing down on those buried faults. We're talking about additional billions of tons of weight being added in a span of just a few months. Imagine adding billions of tons to the weight sitting on top of locked fault plains. The earthquake machine had just been fed a massive dose of fuel, and the stress on those fault zones spiked immediately. Not gradually. Immediately. As the weight of water transferred to the rock below, stress values that had been stable for years suddenly increased. That creates the conditions for rupture. That's how reservoir-induced seismicity works. The weight goes on, the stress spikes, and the faults respond. Scientists have seismometers all around the lake recording this activity in real time. But here's where the story gets truly insane. In 1869, a magnitude 6.5 earthquake struck the Lake Tahoe area. This is documented. It happened. People felt it. Buildings shook. Damage occurred. Ships on the lake reported massive waves. It wasn't even the biggest one possible. The West Tahoe Fault, based on rupture records and geological evidence from paleoseismic studies, which is the fancy term for studying ancient earthquakes through digging into the earth and examining the geological layers, last ruptured between 4,100 and 4,500 years ago. When it did, the magnitude was probably 7 or higher, much higher. Geologists have analyzed the rupture surfaces. They've dated the material using carbon-14 and other radiometric techniques. They know how much displacement occurred. Scientists estimate that a magnitude 7 event happens beneath Lake Tahoe roughly once every 2,000 to 3,000 years. Let that sink in. Once every 2,000 to 3,000 years. That's the recurrence interval. The last one was 4,000 to 4,500 years ago. We're overdue. That means statistically, we're due. Not someday. Now. In the next earthquake cycle. Any moment. And when that earthquake comes, when the West Tahoe Fault finally ruptures again, the consequences will be written in water. The West Tahoe Fault is capable of vertical displacement exceeding 5 meters, 16 feet, in a single rupture event. That kind of movement beneath a lake of this size doesn't just create earthquakes. It creates tsunamis. It destabilizes underwater slopes. It can trigger massive landslides that dwarf the shaking itself. The rupture would be catastrophic, and we've just loaded the fault with billions of tons of additional stress. The timing is terrible. We've filled the lake to near record levels right when the fault should statistically be getting ready to rupture. Climate patterns could drive even higher water levels in the future. The McKinney Bay landslide 21,000 years ago offers a terrifying glimpse at what's possible. A massive underwater slope failed during an ancient earthquake. Geologists have mapped the scar. They've studied the debris field. They've traced the flow of material down the lake bottom using sonar and diving surveys. The evidence is unmistakable. 12.5 cubic kilometers of rock and earth exploded into the water. That's rock and sediment that had been stable, sitting on the lake bottom until an earthquake shook it loose. The displacement created a tsunami that reached 330 feet high. Think about that. 330 feet. A 33-story building. A tsunami that tall pushed water across the lake and over the shores. Imagine water 330 feet high, moving toward the shore at speeds exceeding 100 miles per hour. House-sized boulders, actual boulders the size of multi-story buildings, traveled down the Truckee River. You can see them today, massive rocks, moved miles downstream from where they originated. Some of them are still visible in the landscape. Scientists have followed the path of these boulders and tracked them all the way to the Nevada border. The wave pushed the lake's water level down by 33 feet, temporarily. All that water had to go somewhere. It rushed over the outlets and downstream, creating a second wave that traveled hundreds of miles down the Truckee River Valley. The megatsunami scoured the landscape. It's one of the most violent events to happen at Lake Tahoe in recorded history. Geologists even found sand deposits from this ancient tsunami far down the Truckee Canyon. That's what one ancient earthquake did when the lake held less water and the faults created smaller displacement. Today the lake is even fuller. which means the next rupture could be even worse. The McKinney Bay area still has the same steep slopes, the same earthquake-prone faults, the same potential for failure. The same conditions that caused failure 21,000 years ago are still present. Or the next massive landslide could occur somewhere else around the basin. There are other steep underwater slopes, other fault-controlled topography, other zones of instability waiting. We know these conditions exist. We know the faults are there. We know the water is there. What we don't know is when. And that uncertainty is where the real fear lives. The mystery is what keeps geologists and seismologists awake at night. Over 150,000 people live around Lake Tahoe. South Lake Tahoe, with its casinos and resort infrastructure, casino floors packed with thousands of people at any given time. Incline Village on the Nevada side, filled with luxury homes valued in the tens of millions of dollars. Tahoe City, the hub of the North Shore with its tourism infrastructure. Kings Beach, Crystal Bay, all of them are on the shore or within the blast zone of a potential tsunami. The lakefront real estate is worth billions of dollars. Billions. Luxury resorts, casinos, residential communities, marinas, golf courses, hotels. Everything depends on the implicit assumption that Lake Tahoe is stable. It's not. It never has been. The geological record shows periods of extreme earthquakes, landslides, and tsunamis. But it also shows something else, something that matters right now. The record shows that high water levels in Lake Tahoe correlate with increased seismic activity. More pressure equals more stress on the faults equals more earthquakes. It's not just theory, it's documented in the paleoseismic record. Paleoseismologists have dug trenches across the West Tahoe Fault and studied the record of past ruptures with incredible precision. They count the layers of sediment. They look for the markers of ancient earthquakes. The pattern is clear. More water meant more ruptures. Less water meant fewer ruptures. And we've just pumped the lake to near record levels. If you're watching this and you live on Lake Tahoe or you're planning to visit, that's not a reason to panic. That's a reason to understand what's underneath your feet. That's a reason to know what the geological literature actually says. That's a reason to recognize that the most beautiful places on Earth often sit on top of the most dangerous geology. And that's a reason to be prepared, not terrified. Prepared. The earthquake machine at Lake Tahoe isn't new. It's been running for hundreds of thousands of years. It's been running quietly, mostly, with occasional catastrophic ruptures that reshape the landscape. But here's what's changed. Humans are now living directly in the path of that machine. We've built permanent communities. We've invested billions of dollars. We've created infrastructure that depends on the assumption of stability. We've built power plants nearby. We've built dams that depend on geological stability. We've built casinos that operate 24/7. Hotels packed with tourists. Homes worth tens of millions of dollars. Restaurants, hospitals, emergency services, all positioned right where a tsunami from a major earthquake could strike within minutes. And now, we've just added fuel to the machine by flooding the basin to near record levels. The water level is higher now than it's been in over 20 years. That's millions and millions of tons of additional stress on faults that were already loaded. Scientists are watching. Seismometers around the lake are recording every tremor. USGS researchers monitor the faults continuously with networks of instruments placed strategically around the basin. They have stations on the west shore, the east shore, north and south. They're listening. The faults are waiting. And the lake, that stunning, pristine alpine lake, continues to press down with the weight of 151 trillion gallons, stressing the ground beneath it, minute by minute, hour by hour, day by day, waiting for the pressure to finally find release. The stress accumulates. The pressure builds. The fault plane becomes more loaded. The breaking point isn't a question of if anymore. It's a question of when. And when it comes, people need to know what's happening. They need to understand the mechanism. They need to be ready. The geology isn't changing. The water weight is increasing. The stress is building. Every day that passes, the loading continues. Every heavy rain, every continued snowmelt feeds the lake. And with each increment of water, the stress on those buried faults increases. And if this story reminds you that even the most beautiful places on Earth carry hidden danger, download our free 72 Hours Disaster Guide. The link is in the description.